Section 5.2 is random variables and probability distributions. Let's get those definitions. Miss Arlie, what is it? Well, it was there, and talking to the person behind you isn't going to bring it to you. So, ixnay. A random variable is a variable, typically represented by x, that has a single numerical value determined by chance for each outcome of a procedure. Now, the procedure may be that I'm going to flip a coin 100 times, and x could be the number of times it lands on heads. Or the procedure could be that I'm going to I'm going to survey everybody in here about your birthday, and X will be the number of people who were born in February. All right, so X is just a variable. It stands for something. It's a number determined by chance for each outcome of a procedure. A probability distribution is a description that gives a probability for each value of the random variable and often is expressed as a graph, a table, or a formula. Now, we talked about frequency distributions. These are going to look very similar, but we've talked about frequency distributions. This is a probability distribution, and I'm going to list all possible outcomes. Now, if there are 30 people in here, what are the possible answers to how many of you were born in February? What are the possible answers to that question? 30 or 0 or 1 or 2, anything between 0 and 30 could be the answer to that question. So if I was going to make a probability distribution like my frequency distribution, I would have to list 0 through 30. Those are the possible answers to the question, how many of you were born in February? And then I'd list the probability of each event. Sometimes the probabilities are the same for each event. Sometimes they're not. This is the one slide that I added, the one that you don't have, but it's okay. I just wanted to show you the difference between a frequency distribution, which we've already talked about, and the probability distribution, which is the main thing we're talking about today. A frequency distribution is, remember that table that lists all the possible outcomes and then the frequency of each outcome? This is rolling a die 60 times. And it looks like 8 times it landed on 1, 12 times it landed on 2, and so on and so on. That's the same kind of frequency distribution that we talked about. Gosh, I think that was chapter 2. Well, the difference between, one other thing, a frequency distribution gives the observed frequency of all possible outcomes of an event that's already occurred. We've already conducted an experiment or had a survey. These are showing the results of something that's already happened. That's descriptive statistics. When we make a prediction or when we give the probability of each possible outcome, that's called a probability distribution. And it gives us the probability of each possible outcome for an event that may occur sometime in the future. The requirement, let me go back. If this is the list of all possible things that could happen when you roll a die, it could land on a 1 or a 2 or a 3 up to a 6, and those are the only things that can happen when you roll a 6-sided die. And if this is their probabilities, what do those probabilities have to add up to? If this is the only possible outcomes, the probability that a die is going to land on either a 1, 2, 3, 4, 5, or 6 is 100% or 1, because that's certain to happen. Have you ever rolled a die and it just landed on an edge? Not going to happen. It's going to land on one of those 6 sides. And if you have a fair die, each one of the 6 sides has the same probability. So the 2 requirements for a probability distribution are the sum, remember this symbol, the sum? The sum of all the probabilities is 1. If this total doesn't add up to 1, then it's not a probability distribution. The other requirement is that each individual probability has to be between 0 and 1, inclusive, has two equals right there, because if each value in the right-hand column is not a number between 0 and 1 inclusive, then it can't be a probability. That was our definition of probability. Probability has to be between 0 and 1 inclusive. I love that picture. The parameters of a probability distribution. Ooh, remember the difference between parameter and statistic? Statistic refers to a what? It's a measurement of a characteristic of a sample, and a parameter is a measurement of a population. So that's why we're using mu for the mean here and sigma for the standard deviation. Ooh, remind me what sigma squared is? The variance. Good. This is the population mean, population variance, population standard deviation. I just wanted to show you how ugly those formulas were to make you give your calculator a hug before you go to bed tonight. We're not going to do any of that by hand. This is how those formulas make me feel. Let's talk about how to find the mean, the variance, and the standard deviation for a probability distribution. This probability distribution is a group of 5 babies are randomly selected. Going to run in the nursery and grab 5 babies. What are the possible answers to the question, how many of those babies have green eyes? I grab 5 babies. What are the possible answers? 5 or 0 or 1 or 2 or, yeah, 0, 1, 2, 3, 4, or 5. Those are the only answers that make sense to that question. If I grab 5 babies and say, how many of them have green eyes? Either none of them do, or all of them do, or something in between none and all of them do. Now, green eyes are kind of rare. So this gives the probability of no babies having green eyes. I could grab 5 babies, and there's more than a 50% chance that none of them are going to have green eyes, because green eyes are kind of rare. There's about a 36% chance that only one of them would have a green eyes, about a 10% chance that 2 of them would. The chances that 3, 4, or 5 of the babies would have green eyes is very, very low. It would be very odd if you just went in a hospital, grabbed 5 babies, and all 5 of them had green eyes. That's a shocking phenomenon. That's what this 0 with the little plus beside it means. You can't say that it's technically impossible for all 5 babies to have green eyes. It's not impossible, but it's very, 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 very unlikely. And that's what 0 with a plus beside it means. Almost 0. All right, so we want, number 1, is this a probability distribution? What 2 criteria have to be met in order to say, yes, this is a probability distribution? 2 things. All these probabilities have to add up to 1. We could punch them on the calculator real quickly and make sure that they do, but they do. What's the other criteria? I'm sorry. No. They all have to add up to 1. And what about each individual probability? It has to be between 0 and 1. And that is true as well. So yes, this is a probability distribution. So without using those horrendous formulas, I'm going to show you how to find the mean of that probability distribution and the standard deviation of that probability distribution. This mean would tell you how many green-eyed babies to expect if you grabbed 5. If I went to every hospital in the country and grabbed 5 babies, then what would be the average number of babies with green eyes if I grabbed whole bunches of groups of 5 babies? Well, we put the X's and the probability into the calculator in 2 lists. You can put your number of babies with green eyes in list 1, and the probability for each one of those values in list 2. Go ahead and do that. Go to Stat Editor and make list 1 be the X values and list 2 be the probability values. Did you forget yours? I wish I had an extra to hand you. I don't. Yes, for the last one, you don't have to enter the plus. Just say that the probability for 5 babies with green eyes is just 0. Take me just a minute to catch up with you. Yes, because it's practically 0 and you don't have to enter that 0. 0.528, 0.360, 0.098, 0.013, 0.001, and 0. Is anybody missing any of their list and forgot how to put one back? When you first press the Stat button, number 5 is Stat Editor. It puts all your lists back. Just hit number 5 and then enter, and it'll say, okay, all your lists are back now. Technically, it doesn't matter which list you use as long as you remember the name of which 2 lists you use. Now, does order matter here? Would it matter if I had these numbers in a different order? These are probabilities for specifically this number of babies with green eyes, this number of babies with green eyes. So as long as I kept the 0.528 with the 0 and the 0.36 with the 1, it wouldn't matter what order I put the ordered pairs in, but my probabilities do have to match up with each possible outcome. All right, what do I have next? Quit your Stat Editor, just second and quit to get out of there. And then press Stat, move the arrow over one place, and number 1 will say 1var stats. That's what we're going for. Stat, move the cursor over 1, and then choose number 1. One thing that several people left blank on their study guides, maybe it was just because I had it in small print and you didn't notice, but on the study guide I had where to find standard deviation on the calculator and where to find variance on the calculator, because we're going to learn to do so many more things with the calculator. It's good to have on your study guide, hey, where did we find that 1var stats? Or I don't remember where to go on my calculator to find the mean of a probability distribution. So you'll see on the on the study guide, I have a place for write down the steps you punch on the calculator in order to find the mean and the standard deviation of a probability distribution. Yes, ma'am. Oh, can let me show your calculator. Calculators are just like computers, and I didn't know this till a couple of semesters ago, but just like computers and your iPad and your iPhone have updates, They make updates for TI-83s as well. And some of us have, I don't even know which one is more recent, mine or yours, but let me show you what some of these calculators are saying instead of what mine says. And this is absolutely fine. Usually comes in just a second. There we go. So if that's what your calculator is saying, that's absolutely fine. Can I get more? If this is what's showing up on your calculator, you say, I put my X values in list 1. These frequencies, they're not actually frequencies. The calculator doesn't know that you've entered probabilities, but you tell it, I've put my frequencies in list 2, and then press calculate, and you'll get the same thing I'm fixing to get. So Miss Ashley, when I hand this back to you, just make sure you have list 1 here, list 2 there, and press calculate, and you'll get the same thing I do. That's going to happen several times this semester. It's just a different way of entering the information, but it works the same way. All right, for those of you whose calculator did what mine did, just popped up one variable stats, I need to tell the calculator I put that data in list 1 and list 2. And remember, to access those lists, you have to press second list 1, second list 2. Everybody look up a second. There's one other thing you need to know. If your calculator looks like mine, you're going to have to use your comma button. Your comma is right there over number 7. You're going to enter list 1 and then comma and list 2. List 1, comma, list 2, and enter. Now, regardless of which operating system you have, did everybody get this same mean and other stuff? I'm sorry, what? Error? I know what that most likely is. Go back to your, let's see if it'll tell us. No, let's go back and see if maybe, usually when that happens, you've entered more numbers in one list than you have the other. So it could just be a typo in your stat editor. Yep. You left 0 out of the top. So you need to retype list 1. That's something to watch for. When you get an error like that, though, you may not have the same number of entries in both lists. All right. Like I said a minute ago, my calculator has no way of knowing that these are probabilities. The calculator thinks they're just frequencies. Thinks this is a frequency table where the possible outcomes are 0 to 5, and here's how many times a 0 happened and how many times a 1 happened. So the calculator is going to give me the results X bar, like that's the mean of this sample. Well, we know that that's a a probability distribution for a population. And so that's why we're going to write our answer using mu instead of X bar. We're going to write, yes, it is a probability distribution. Its mean is this 0.599, but it's mu instead of X bar. And trying to think if it told us what to round to. It didn't. Let's stick with three digits there. My math lab would tell us 0.599. And what is the standard deviation for this data? Here's where you have to know your symbols. you have to know which one of those things means standard deviation, and it's sigma that means standard deviation. So if we round it to 3 decimal places, it's going to be 0.725. The one other thing you notice at the bottom of my results screen here, it said n equals 1. Again, because the calculator thinks these are frequencies, it's telling me what all the frequencies add up to. If this is indeed a probability distribution, what should all these add up to? 1? It did. So I don't have to type in each frequency, add them up, and make sure they equal 1. The calculator is going to add them up for me. But because of rounding errors, sometimes that can be off just a tiny bit. It could be 0.999 or 1.001. That's close enough. It's just the fact that these are rounded that might cause them not to be exactly 1 sometime. All right. That's the next slide, isn't it? Okay, just making sure. Just like we have identified usual and unusual values before, we want to do the same thing with probability distributions. We want to use our probability distribution to say which values we would consider usual and which values we would consider unusual or shocking. Now, help me remember this real quickly. Our definitions of unusual so far are outside how many standard deviations of the mean? Huh? 2. Yes, I just didn't hear you. Outside 2 standard deviations of the mean, that means the same thing as what about z-scores? What z-scores are unusual? Anything less than -2 or greater than +2. All right, good. You remember what's usual and unusual. And we have found the maximum usual and the minimum usual before. We just have the symbols for population here. The max usual is the mean plus 2 standard deviations. The min usual is the mean minus 2 standard deviations. Anything between those two numbers would be considered usual. Anything outside those two numbers would be considered unusual. So, we have a probability distribution for a p-hybridization experiment. Is that the next slide? I'm not skipping anything? All right. Who's the father of genetics? I'll go tell Miss Fields and she'll be so happy. Yes. I haven't heard it pronounced that way. You could be absolutely right. I've always said Mendel, but we would spell it the same. All right. Probably whether you're from Tennessee or Alabama. No, Tennessee or Alabama is what I'm going to blame it on. Gregor Mendel, father of genetics, did conduct a lot of experiments on hybridizing peas and studying the genetic effects of mixing genes from different peas. That was his whole life. Hybridizing peas. And every morning he would go out to the garden and randomly grab 8 peas and then answer the question, how many of these peas have green pods? That was the question for, 10 years or something. Out of these 8 peas that I grabbed this morning, how many of them had green pods? What are the reasonable answers to that question? 0 through 8. It wouldn't make sense to say I have -2 green pods or I have 10 green pods if I only picked 8. So 0 through 8 are your total possible outcomes. And according to Gregor Mendel's research, here are the probabilities for each of those outcomes. Would you be shocked if you went out in the garden with Gregor Mendel some morning and grabbed 8 peas and none of them had green pods? Would that be shocking? That's unheard of. Not impossible, but highly, highly unlikely. It's highly unlikely that only one of them would have green pods. What is the most common answer to the question, how many green peas did I get this morning? Looking at that probability, 6 had a higher probability than anything else. So, I mean, about 31% of the time when he grabbed 8 peas, 6 of them had green pods. Now, what 2 things have to be true in order for me to say, yes, this is a probability distribution? The sum of all these probabilities has to be 1. What other thing? Each individual one has to be a number between 0 and 1. And that's true, so this is a probability distribution. It's true because I've already added them up and I know they equal 1. All right, enter these on your calculator as list 1 and list 2. We're going to find the mean and the standard deviation just like we did for the other problem. I'm going to let you punch that, and I'm not going to this time. I'm going to play like my math lab and tell you what to round to. Since the number of green peas is always a whole number, let's round our mean and standard deviation to the nearest tenth. That's what we've usually done. We've rounded our mean and standard deviation to 1 decimal place more than the original data. So what are you getting for mu? Well, folks still typing. It's okay. List 1, list 2, stat, calc, 1 variable stats. 6 even? Exactly? 6.0. Okay, cool. That's just looking at the table. That's what we said we should expect more times than anything else because that's the value that had the highest probability. If Gregor Mendel goes out, grabs 8 peas every day for 10 years, then he should expect the answer to how many of these have green pods to be 6. That doesn't mean it will be every time, but that's the average of all the answers to that question. What about standard deviation? What do you get for it? 1.2? Okay, and if we're going to round to 1 decimal place, it would be 1.2. So we can use the range rule of thumb to identify the maximum usual number, what he would not be shocked about, and the minimum usual number, and we could give a range of values that we would consider not shocking. Well, the minimum usual is always the mean minus 2 standard deviations, and the maximum usual is always the mean plus 2 standard deviations. So the minimum usual value would be 6 minus 2 1.2s, or 6 minus 2.4, or 3.6. And the maximum usual would be 6 plus 2 standard deviations, 8.4. So I'm trying to answer this question, identify a range of values that we would consider usual. What would you give for that range of values? No, this is our minimum usual, and this is our maximum usual. Yes, we're considering what's usual. Anything between those two values. That's what minimum usual means. The lowest non-shocking number and the highest non-shocking number. So our non-shocking range would be between 3.6 and 8.4. Except, tell me this, if you walked out to the garden with Gregor Mendel one day, grabbed 8 peas, and said, how many of these have green pods? Would you be shocked if there were 8.4? Why? Because you only picked 8 peas. You can't have 8.4 green pods if you only picked 8 peas. So there have been other times where we had to go, well, that's what the formula says, but maybe in some circumstances a negative wouldn't make sense. In this problem, 8.4 doesn't make sense because you cannot possibly get 8.4 green pods out of 8 peas. So I would list that range as from 3.6 to 8 because you can't get 8.4. Now, technically, you can't get 3.6, but this is an average, and you could get that for an average. Miss Ashley? Don't say that something that cannot possibly happen is non-shocking. By definition of can't possibly happen, it would be shocking if it did. So correct. And that's not going to happen 99 times out of 100. Just on this particular problem, you should always be thinking about what these numbers mean, not just this is what my calculator said, but if you're thinking about what that means, that can't be usual because it's not even possible. All right. This is one of the most confusing things on test, where are we? Test 2. So whenever I see that, I expect to see red ink pens whipping out and highlighters whipping out and somebody writing That's what I do when a teacher says, this is confusing. You're going to have to work on this. And see, I'm setting a trap for you right now. After you've highlighted this and put a star by it and written important and study, on the practice test when you say, I can't get this unusually high problem right, I'm going to say, go back to that slide that you highlighted and put a star by and a couple of exclamation points and read it again. Any problem that says unusually high or unusually low, this is what you need to be looking at. X successes among N trials is unusually high if the probability of X or more of those things is less than 0.05. In other words, we have a new definition for unusual. we're going to consider unusual anything that has a probability of less than 0.05. Really, that's not new, though, because we already knew that what percent of the population lies within 2 standard deviations of the norm? Of the mean, I mean? 95. So what percent lie outside that? 5% written as a decimal is 0.05. So anything that has a probability of less than 0.05, that's just another way of saying anything outside 2 standard deviations of the mean. But the kicker is remembering that this is not just the probability of X is less than 0.05, it's the probability of X or more. If we're talking about is 5 out of 9 babies with green eyes unusually high, you wouldn't just look at the probability of 5, you'd look at the probability of 5 plus 6 plus 7 plus 8 plus 9. You got to add up some probabilities to answer these questions about unusually high or unusually low. I think I've said this, but just in case I haven't, have I told you you get to use a note card on the test from now on? And you were going to remind me if I forgot, right? A 3x5 card, not a poster, not a piece of paper, not a 4x6, a 3x5. You bring a 4x6, I'm going to take my scissors to it and whittle it down to size for you. 3x5, front and back, microscopic writing, anything you want on there you can bring with you. Because what's important here is not that you memorize a bunch of stuff, but you already have enough vocabulary that if you forgot what a frequency distribution is, but you remembered the words, you could always Google it, right? You don't have to memorize everything on the internet. You just have to have enough words to describe what you're looking for so that you can find the answer online. And that's why I don't mind you having a card. You don't need to memorize a whole bunch more stuff. If you don't understand this pretty well, a whole poster wouldn't help you front and back. If you don't understand it, all the scribble in the world is not going to help you. So you work just as hard to understand. I'm just saying you don't have to memorize. So on my 3x5 card, I would have unusually high probability of X or more is less than 0.05. And I would have unusually low probability of X or fewer is less than 0.05. Here's the problem that gets folks on the homework and gets them on the practice test and gets them on the test. And they all go back to this slide we just highlighted all over. Based on the Gregor-Mendel table that we had, find the probability of getting exactly 3 peas with green pods. All right, exactly 3 peas with green pods. What's that probability? You just read that straight off the table. If you want the probability of exactly 3, it's 0.023. Probability of 3 is 0.023. Now, how are we going to find the probability of 3? Probability of 3 or fewer? Add up the probability for 0, 1, 2, or 3. That's what 3 or fewer means. If you add up these 4 numbers, you get 0.027. If I want to ask the question, is 3 an unusually low number of peas with green pods? Do I use the probability of exactly 3 or the probability of 3 or fewer? Look back at the previous slide that you just highlighted. For unusually low, use the probability for 3 or fewer. Don't use the probability of exactly 3. Use the probability of 3 or fewer. And we have already found that to be 0.027. How does that compare with 0.05? Less than, greater than, equal to? Less than. If the probability of 3 or fewer is less than 0.05, then is 3 an unusually low number of peas with green pods? Yes. Now, on this particular problem, you would have said yes, no matter which one of those you were using, they're both less than 0.05. So on this problem, it wouldn't matter, but on another problem, it's very likely to matter. And make sure you're using 3 or fewer instead of exactly 3. If I said, is 5 an unusually high number of peas with green pods? Would I use the probability of 5? 5 or more. I would add up this, 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 and this. That would be way more than 0.05, so no, 5 wouldn't be an unusually high number of peas with green pods. All right. Yes, ma'am, you're allowed. Okay, I can write something down for you there. The probability of 3 or fewer is the probability of 3. What does OR tell you to do? Plus the probability of 2, plus the probability of 1, plus the probability of 0. Because the probability of 3 might be less than 0.05, but the probability of 2 might be high. You couldn't say 3 is unusually low if the probability of 2 is high. You pretty much, I mean, if that made sense, yay for both of us. If it didn't, then you need to make sure you have that on your index card. For unusually high, you use X or more. Unusually low, you use X or fewer. All right, one other thing in 5.2. Actually, there's this and then one more example. The expected value. Now, going back to that Gregor Mendel screen where I found the mean number of green peas, where was it? Right here. When I found the mean number of green peas to be 6, what did I say about that 6? What does that actually mean? And that's a different mean than this mean. I said that's how many he would expect. If he went out and grabbed 8 peas every morning for 10 years, this is what he would be expecting. So it's not surprising then that the formula for expected value, if you look back to the picture of the scared llama or the confused llama, that's the same formula for the mean of a probability distribution, because those two things mean the same thing. The expected value is the mean. So sometimes I may say, find the mean of this probability distribution. Sometimes I may say, find the expected value of this probability distribution. You just have to understand those are two different ways of saying the same thing. So you could put right here that, if you thought it would help. The mean is the same thing as the expected value. Miss Tiffany, smile. Life is pretty good. All right. Last problem in 5.2 is expected value. And I have to go, wait, that means the same thing as the mean. I'm going to sell a bunch of life insurance policies, and I want to know what to expect for the profit for my company. If I can set up a see, it didn't give me a table here. I'm going to have to come up with my own table. But if I can come up with a probability distribution, then I know how to put that in list 1, list 2, and find the mean. And the mean's the same thing as the expected value. So the hard part of this problem, two things have to trigger in your head is, hey, this means make a probability distribution. And second thing is, and find the mean. I think those are good enough words to put right here. Ooh, I'm glad you said that. I'm glad you said that. Let me finish writing this sentence and I'll answer you. Make a probability distribution and find the mean. Because mean is the same thing as expected value. From here on out, we're going to do almost everything we do on a calculator. I can think of 2 formulas the rest of the semester that we don't have a button for on the calculator, and we're actually going to have to enter some stuff by hand, and that's fine. But my math lab, because it was written for teachers who do show calculators and teachers who are mean, I take that back, they're not mean, they just want you to really, really get it. Teachers who don't use a calculator, everybody listen to this is important. From now on, View Example is going to show you how to do it by hand. And if one of you emails me and says, I wish I could get to that llama real quickly. If you email me a picture of yourself and you look like that llama because you're trying to use the formulas, I'm going to say, stop trying to use the formulas. You can do this on the calculator. Now, what it's good for, Ashley, is you can check and make sure you have your probability distribution set up right. Or on some other problems, you can make sure that you've chosen the right variable, the right value for all the variables. But when they start talking about doing this formula by hand, click out of View Example. We're not going to do it. Unless you just want to. And you can. That would be okay. All right, let's see what this problem is about. There is a 0.9968 probability that a randomly selected 50-year-old female lives throughout the year. That makes me really happy because I turned 49 last week. If I make it to one more birthday, there's a 99.68% chance that I'm going to make it to one more birthday. All right, I'll make it. If I make it to 50, I'm probably going to make it to 51. Not 100% sure, but probably. A Fidelity Life Insurance Company charges $226 for ensuring that the female will live throughout the year. Now, let me give you a spelling lesson here. This insuring is buying insurance. What's the other insuring? With an E, that would mean they're going to make sure she lives. Well, they can't make sure she lives, but they can sell her a policy in case she doesn't. That's the insuring with an I. So the company's going to charge $226 for ensuring that the female will live through the year. If she does not survive the year, the policy pays $50,000 as a death benefit. So if she dies, family's getting some money, but they're too sad to spend it. Okay? Don't think everybody's dancing around because this 50-year-old woman died. Let's make a probability distribution. What are the possible outcomes for this woman in the upcoming year? What are the two things that one of the two is definitely going to happen? She's going to survive or she's going to die. That's the only two things that can happen, nothing in between. So I'm going to make my probability distribution. I'll have to write small, but my probability distribution always has the possible outcomes in the left column and the probabilities in the right column. And if I want to label this even more clearly for myself, I can say, this is the event where she lives, this is the event where she dies. What is X going to stand for here? What? Those aren't numbers, though. X can't, what? Those are numbers, so you're getting warmer. Tell me words for the numbers you just said. You're talking about the probabilities. The probabilities go here, and we will put them here, but that still doesn't tell me what X is. Binary system, computer programming. Yeah. No, it's the amount of money. It's the possible outcomes. If she lives, she's actually going to lose $226. She paid $226 for the policy. So if she doesn't die, she's just out $226. Is she sad about that? No, I'd rather be out $226 than be dead. Miss Ashley? Yes, and she can renew it every year. Every year she can decide whether to pay $226 for next year. But as she gets older, it may go up. Yeah, it may not always be $226. All right, so this X value is the, let's say, monetary value for each outcome. If the outcome is that she lives, then the monetary value is negative 226. Now, I only know this because this problem said from the perspective of the female. From her perspective, living has a negative monetary value. If it said from the perspective of the company and she lives, they would have made money. They would get to keep her 226. But since this says from her perspective, living is a loss of money that we're gladly give up. Now, while we're working on our X's, what's the monetary value of her dying? $50,000. She still spent the $226. Man, nothing in real life is simple. We left simple behind in algebra. If Bob is 3 years older than his brother Joe, we've got to say, I'm trying to assign it some words so it'll make sense when you look at it at home, because I know you look at it at home. Net value of dying. I hate to call it that, but that's what it is. Yes, the estate gets $50,000, but $226 was already taken out of the estate. So really, the net value is $49,774. Watch out for that. $49,774 is the actual change in the estate's value that year. Everybody okay with both of those X's? All right, what about the probabilities? What is the probability that she's just out $226? That 99.68%. She's probably going to live, and so she's probably going to lose $226. What's the probability that the estate gains $49,774? And where did you get that? There's only two possible things that can happen. If there's 99% chance of living, then there's a 1% chance of dying. These are complements of each other. These are the only two things that can happen. So 0.0032 is the probability that the estate is going to gain $49,774. Another thing that I know is if this is a probability distribution, these have to add up to 1, and that tells me how to find that one. Subtract this one from 1. All right. Is that a good probability distribution? We have the only two possible outcomes. These two probabilities add up to 1, and each one of them individually is between 0 and 1. So I've been working this problem so long, I don't remember how to find expected value. What do I do? It means the same thing as the mean, and how did we find the mean? Somebody say One Bear Stats. It was stat, calc, and then One Bear Stats. We have to, because otherwise we would be indicating a gain for the estate either way. See, actually, sometimes some problems, negatives don't make sense, but in some problems, negatives do make sense. All right. Ooh. It's so much easier to enter stuff on the calculator than it is to use a mouse to enter it. I'm going to use that for my excuse for why I'm so much slower than you. I'm using a mouse. Oops. Yep. Got it. See, Miss Ashley, email me if you need me this weekend, and look for an email from me when I hear from my dean. I will be checking. All right. Do I have that entered correctly? And how do I find the mean? Stat, calc, and number 1. Let me clear that. Stat, calc, and number 1. And then I'm going to tell the calculator, I want you to use my list 1, comma, my list 2. and which one of those numbers is the expected value of this, let's say 1,000 policies are sold. What's the average gain or loss for each woman? On average, each woman will lose $66. Now, actually, you can't lose $66. You're going to either lose 262 or whatever it was, or you're going to gain 49. There's really nothing in between. But the average of 1,000 policies would be a $66 loss. You could put, it just depends on how my math lab asked the question. If it says, what is her expected value, you would put negative 66. If it was multiple choice, you'd probably say it's a loss of 66, because those two things would mean the same thing. Yes, ma'am. Double check your numbers then. Just about the only way you could have something different is if you transpose two numbers in your stat editor. Did you have the negative with the 226? That's easy to do. Easy to do. Now again, this $66 loss is from the perspective of the woman. From the perspective of the company, what is the expected value? If every woman loses $66, then the company is going to get that $66 for each policy. So that's how they decide how to set policy premiums. You take the probability that you're going to live or die and decide how much profit you want to have, and then adjust the premium accordingly so that that expected value is what your company wants it to be. Yes, ma'am. Absolutely. The probability that an 18-year-old will crash versus the probability that a 30-year-old will crash. And that's why insurance is cheaper when you're 30. Exactly the same thing. Probability that you don't go to the doctor versus probability that you do go to the doctor. Right. They've broken, I mean, they can't say with any degree of certainty whether you're going to have to be in the hospital. Right. But they do consider risk factors. You know, if you check the box, yes, I'm a smoker, then your policy is going to be higher because the probability that you're going to have both lungs removed is higher. Yes. I think the evidence is there.
Well, yeah, I mean, that's an obvious one. Yeah, I know that much. Like, for example, let's say it's I have a Porsche, and it's Bob that has a Ford truck.
The Farm Bureau has a computer program that spits out Bob's probability of crashing versus your probability of crashing. I don't know what all factors go into that program, but I can tell you that the career that does all of this number crunching and predicting probabilities, that's called an actuary. That is one of the hottest fields hottest fields going. As life gets more complicated, we want more people to tell us the probability that things are going to be okay, or the probability that things aren't going to be okay. That's what an actuary does. And I mean, if you like statistics a little bit, pursue it. Either you'll come to like it more or come to decide that's not what you want to do. Engine.
If a guy is married versus a girl that isn't,
the formula would be very complex, and that's why it's a computer spitting out those probabilities and not somebody doing it by hand. Okay, I was just going to say, if this said from the perspective of the company, then that would be a gain of 66 instead of a loss of 66. So can the company expect to make a profit from these policies? Yes. 66. Ooh, that looks like a negative. Let me draw an arrow. Yes, $66 per policy. So if they sell 1,000 of these policies, they're going to make $66,000. It's not bad. They're going to have to pay the families of a few women who died, but still all the 262s they collected outweighed what they paid. And that's the only way insurance can stay in business. All right. There's a problem like this in the homework, and it has one other part. Let me just call it. I'll tell you what it's going to say and how you'll figure it out. It says, what should the policy cost if the company just wants to break even? Yeah, using everything we've already done. We don't have to redo any crunching. We just have to think of how to get this answer. This is one of the worst problems to click view example. The first time a student said, I don't know how to do the D part, I was thinking, well, gosh, I don't either. So I clicked view example, and I have a master's in math, and it didn't make any sense. Or it did eventually, but it was the hardest possible way to figure out something that really is simple to do. Can anybody think of the simple way to figure out what the company should charge if they don't want to profit, if they just want to break even? It would be nice if Obamacare just broke even. How much would you pay for the policy? I want you to click view example just to see how difficult they made that. If at $226 they're making a profit of 66, then just charge 66 less and break even. I just want you to see. I want you to click that view example button and then write the editor. 226 minus 66 is 160. So if you charge 160, the company will break even.